Hello everyone, this is Z. I'm a PhD student majored in computer science in Southern Methodist University of Dallas, Texas, in USA. I'm gonna to upload several videos to show you my created visualization programs like this for my research work. I study algorithm in graph theory area, especially on graph partitioning problems. And I also study the graphic coding in visual arts, which is a creative computational area. So my research interests focus on combining the two areas together to create animation programs to reflect the performance of the algorithm implementation, which is a kind of algorithm engineering work. So I termed it as visualized algorithm engineering. This video would talk about one of my projects, which is bipartite grid partitioning of a random geometric graph. The application usage of this problem is on the wireless sensor networks. So I also call that wireless sensor network project. And this video will focus on talking about just an overview of the project, like what the project described, what's the problem it tried to serve, and how I use the animation program I created to help demo the whole project algorithm procedure and how it works. So that's a video I'm gonna to create. Then my supervisor is Professor David W. Matula. That's his personal webpage, and this is my personal webpage. And I use a language called processing, which is a really famous language in creative computational area to create the whole program. So let's talk about the project now. And first of all, let's directly go to the background part, because the title is pure academic one. And the wireless sensor network is actually a network composed of wireless connected sensors. And each sensor can detect some information surrounding it. So if you collect all the data from all the sensors, so you can actually have a bunch of sensors and throw them out into a region. Then if you collect all the data, all the information collected by the sensors, then you basically monitored the environment of the region. That's why the application for wireless sensor network is for monitoring and recording the physical conditions of the environment and organizing the collected data at the central location. So, but the following question would be how you collect the data from all the sensors. Since each sensor will have their own data, then one cost-effective way is like you create a backbone network in the sensor network to relay all the data information to some specific sensor node. We call it gateway sensor node. So like this sensor collects some data and relays the data to this sensor, to this sensor, to this sensor, and finally to the gateway node. Then we can collect the data from the gateway node. So the route here, and we can call it backbone route, then we can create a following like a backbone network inside. So then how you create the backbone network? So you actually you can manually create that like you manually create the hexagon lattice one and the Cartesian lattice one and maybe other lattice one. It's fine. But the problem is the wireless sensor networks are composed of many cheap sensors. They are low power, easy to be broken, or even easy to out of power. In other words, like you have a bunch of sensors throughout to the region, maybe partial of them not working. So that will cause your created backbone network disconnected. Then you cannot get all the data again. So that's why we need some algorithm to automatically create or construct the backbone from the sensor network. And the algorithm also require efficiency, because if partial nodes broken or partial nodes not working, then we can recreate a new backbone from the remaining sensors instantly. That's basically what my project try to simulate. So I use graph theory way to model the program. Like I use the node to represent each sensor. And because each sensor are wireless connected, and their connection limited by the distance, so they can only connect it if they close enough. So that's why for any pair of nodes, if they are close enough, then we connect them together. Though in graph theory, it's called a random geometric graph, and the nodes are randomly distributed in the region. That's why the whole project called like a partitioning of random geometric graph. Okay, so before continue that, I directly use my program to show the whole procedure. And so first of all, let's imagine we use a unit square to describe the whole procedure. So like we can say, okay, we throw out 10,000 sensors. Then we give a threshold, how much distance is a threshold for their connectivity. Like if I say 0.057, in other words, if any pair of nodes, the distance of any pair of nodes are less or equal to 0.057, then they are connected. The reason I choose the number because it estimated average degree is about 100. So then we can deploy the whole program. Then so first of all, like I mentioned, we throw out the sensor. So in the program, actually, we random distribute the node in the area. So this is a unit square area, so the length is 1. And then we can control the... Oh, it's finished. Okay. So after we get to the sensors, then we need to construct the graph. This is actually a sub-question about the project, like how to construct the random geometric graph in an efficient way. Of course, you can use exhaustive way, like here I can use the exhaustive method to create the random geometric graph. Then it's working, but it's slow. So it took a long time to finish. Of course, I can control I can increase the speed to enlarge the display interval, because for a computer program, the most resource-consuming feature is still the display. So if I increase the display interval, then it's faster. Then, okay, that's one way. Then another way is we can divide the whole region into slice, like we divide the regions into vertical slice, and we only need to the width of each slice is the threshold R. So then we only need to check all the nodes in the slice region. If any pair close enough, then we connect that. So we call this sweep method. Okay, so then we can demo this in this way, like my program shows. So we can scan from left to right. That's what it does. Okay, so that's another way. It's more efficient. And there's another even more efficient way. We call it cell method. It's also divided the region, but it's divided in the whole region into cells, like here it shows. Then we don't need to scan all the nodes in one slice. We only need to check the nodes of current cell and the nodes of surrounding cells. So if any pair close enough, then we connect them. And then we can use a program to show the procedure like this. So you can see it's faster than the former two methods, and of course the sweep method is faster than the exhaustive method. So that's actually showing the performance difference of the different algorithm applied on the same question. So that's for the network, or you can say graph generation part. And then after we generated the graph, then we get into the main problem, how we create the backbone subgraph of the whole sensor network. There are many ways. So what we use is we try to determine the independent sets. I actually divided the whole project into 4 procedures. The first one is creating the random geometric graph, which we already did here. So then we determine primary independent sets, and then we determine relay independent sets. Finally, combine the primary and the relay independent sets together, we create the backbone. So what's the meaning of independent sets, first of all? So independent sets is a subgraph of the current graph which does not have any edge. In other words, it's just independent nodes in the set, and we extracted the nodes from the original graph which not connected with each other. So that's actually an independent set. So why we combine 2 independent sets could establish a backbone? Then let me directly show you the example from the manually created backbone. So here, so like the hexagon lattice, like if you focus on the blue node here, you can see all the blue nodes not connected to each other. Same situation happens on all the red nodes. So all the blue nodes are one independent set, and all the red nodes are another independent set. Then you combine them together, it's a backbone. So you can relay information from the 2 independent sets. That's why we only need 2 independent sets to construct the one backbone. Right. So okay, then the following question would be how we determine independent set from a graph. There are many ways, but here what I use here is actually called smallest last coloring algorithm. Okay, so this coloring algorithm is actually from the smallest last ordering algorithm from my supervisor, Professor David Matula, and one of the former student of my supervisor also published papers like this to argue why the smallest last coloring algorithm is the most efficient way to generate the independent set in this case. He used a different way to create backbones from mine. He just use smallest last coloring algorithm to generate several independent sets. Then he used the independent sets itself to create a corresponding backbone. So I use actually 2 independent sets to create one backbone, and under the first primary independent set I use the same way, like to use the smallest last coloring algorithm to generate. Then I use the recoloring algorithm I created to generate the relay independent set. Then I combine them together. So that's the whole procedure. So let me show how to perform the smallest last coloring. So the smallest coloring actually has 2 procedures. One is doing the smallest last ordering algorithm. So the smallest last ordering is simple to describe. Like each time you try to delete the minimum degree node from the graph and push the node into the end of the order. So that's generating a smallest last order of the original graph. So in my program, it shows like here, this is still the original graph, and if I show you the whole graph, it's like this. If I not delete the edge, it's actually only show the nodes. then the measurement here means like the green part is highlighting the nodes of the minimum degree. The red part is highlighting the nodes of maximum degree. In this case, actually, we have three vertices have the same maximum degree 134. Then only one vertex has a minimum degree 23. So if we perform the smallest last ordering, you will see it's shrinking from the boundary because it's keeping deleting the node of minimum degree. So that's a procedure to show how the algorithm work. Then, okay, after we performed the smallest last ordering algorithm, then we would get the order in the program. Then we proceed to the coloring. Then the coloring actually is a greedy coloring way. So you scan from the order we just got. Then from the first node of the order, we try to check all the neighbors of the node to see whether there's any assigned color for the node. If not any, we assign the first color. If there's other colors of its neighbors, then we try to assign the smallest color to the current node. That's why it's called smallest coloring. So, but if we perform the algorithm in the program, you will see it's a reverse order. It's a reverse procedure of the smallest last ordering, like this. So, yeah, I can increase it. So it's finished. Then after that, because we try to assign a color different from all the neighbors of the current vertex, right? So each color is actually an independent set of the original graph. So we color that, we can actually show the independent set of each color. So smallest last coloring partite. I call this partite. So this is the first color. We have 52 colors here at all. So we have this color, so you see it's not connected from each other. So that's all the colors. Okay, so technically we got so many independent sets. I mentioned we only need 2 independent sets, then we can construct a backbone. So technically we already can construct several backbones. Like I can show you here, like a smallest last coloring bipartites. It's called a bipartite subgraph in the graph theory. So that's actually use the first color combined with second color together, and you have the backbone generated. Okay, so but the problem here is not, guaranteed to create a really well robust backbone subgraph. So like here, so we create independent set, right? So if we combine any 2 independent sets together, it may have a distort problem. In other words, okay, though this case shows you it's a well-connected backbone network, that's good for backbone usage. But if other cases, like I can show you here, yeah, this like this case. So the red color is one independent set, and the maybe called same color, yeah, the kind of light blue color here or same color here is another independent set. So if you combine them together, you see it's all disconnected components here. So it's definitely not good for using as a backbone network. So it's a distort problem. That's why I have following procedure. So from this, so up to now, after we proceed the smallest coloring part procedure, so I actually can draw a plot, which called a color size plot. So we would find a feature from the smallest coloring algorithm, which is, so this is color size plot, which means like how many nodes each color, in other words, each independent set has. Then we draw a plot. So you will see it always follows this scheme. In other words, like the first several color sets will have a fairly same color size, node size. In other words, they are fairly flat. Okay, so it means like you have almost a similar amount of nodes for each independent set. Then after first several color sets, then it starts dropping, and in the end it goes to the minimum size. So that's why I can select the first several color sets as the primary independent sets, then use all the remaining to reuse all the remaining vertices and to recolor them for pairing up the first several primary color sets. So that's why I call the first several color sets as the primary color sets I selected. Okay, so that's how to determine the relay coloring procedure. So yeah, so I have the partitioning procedure here. In other words, you try to select the first several color sets which occupy the 55% nodes of the original graph. So you also can adjust. So normally we choose around 50 or 55, like this. So you can do the 55, then you proceed. Then it's try to select one color set by another. And when you select them, like you calculate how many vertices it occupies by far. Then if it achieved the 55%, it stop. So that's a simple way to select the several first color sets. So now it's finished. So these are all the primary sets. Then for the relay color, so then we can recolor all the remaining vertices, all the remaining nodes to pair up. So this color algorithm is we created a new algorithm different from the formers. So which is you try to it's still a Grady coloring way, and you try to color it pair up with the first selected primary sets. So let's deploy the algorithm first. It will like this. Okay, now it's stopped. So then after this, we can combine the primary independent set and the relay independent set together and generate the backbone. Then we will have several backbones available here. So here we have generated we have generated 21 backbones here. So you can see all the 21 backbones are really well connected. Only a little, actually all of them are really well connected. That's a result. So even though some of them not covered all the original graph, so you can use a region to show how much it covers. So that circle means like this node covers how many nodes in the original graph. So if you put all the regions for each like a node, you will see it's basically covered all the original graph. So it also shows here in data like a 100% coverage, but it's not all the case the worst case is actually not so bad using this way. Let me see. Okay, so let's see. Let's choose one not. And also, of course, another issue, you need to delete the minor components. So these are not used as the backbone usage. So you should delete them like you delete the minor components. Okay, so here. Then like, let me choose. Oh, like in this case, this graph actually occupies 99.9% of the original graph. But even though you have some backbone not covering all the original region, then we still have a solution. Like, since these 4 procedure algorithms are all linear time, so they are really fast. So and besides, you use the procedure once, and it will generate several backbones together. Then we can use the several backbones in turn to cover the whole original region. So, and all of them are actually really high domination of the original graph. So we can do that. So that's one thing. And also, if I show you the color size plot again, you will see what's happening for the relay coloring algorithm. So this is original smallest last coloring algorithm. It has a color size plot. Then after we selected the first several color sets, which is this. So that's the original one, and the red part is what we selected. So the remaining part is called relay candidates. It's called relay candidates. So this green part is the relay candidates. We try to recolor all the nodes in the relay candidates to pair up the first primary set. Then finally we got the relay sets, which pairing up with the first primary set. So from the plot you can see the amount of the independent sets on average is actually less than the primary one, but they are corresponding one by one, and the relay set also fairly flat. Then we can combine, for example, we can combine the color 0 to color 52 as a well-connected backbone, one by one together. So that's how it works. So then, and basically these are whole procedures of all 4 procedures of the algorithm in this project. And some other things about the project is, if you pay attention, the former slide here showing the manually created backbones. Like this is a hexagon lattice, this is Cartesian lattice, and this is, we call it biregular 3-4 lattice. So this one is, if you pay attention to the topology, you will see the both blue independent set and red independent set are triangle lattice, right? Then the red independent set is a little bit larger triangle lattice, and the blue one is a little bit small triangle lattice. In other words, the blue independent set more denser, has more density, and the red one a little bit sparser compared to the blue one. So that's exactly what happened in our algorithm. So if I show you the primary independent sets, the primary independent, or I can show you smallest last coloring parted. Yeah. here. You will see that that's a primary independent set. Okay, and you can generate a Gabriel graph for the independent set, and you will see most of them are triangle letters. Not all of them, but most of them are triangle letters. So this is basically like the blue independent set manually created here. And if I should use the relay coloring partites, so that's the first relay coloring. Oh, it's not really obvious to see. So, but I can increase the node size. So this is a first relay independent set. So if I also deploy a Gabriel graph on that, this is also, most of them are also like triangle letters. If we see other examples like this blue one, you can also see that. So this one can corresponding to the red independent set here. So our algorithm actually would get the results similar to the biregular 3-4 letters here. That's what it happens. Okay, so there are several data we collected from the program, and also some plot like the plot showing the degree relation. So the white one is original degree, and the purple one is the smallest degree when deleted plot. Green one is average degree when deleted plot, and the purple one, the pink one, actually, it's the average original degree. So that's a several degree plot. And also we have several like benchmark data tests for different topology from the program. So that's the whole project, wireless sensor network project I did using the visualization program I created. And the next video, the following video from that, I will upload a video about talking about the visual details of the program, because I basically expanded the program into a pure, visualization algorithm implementation tool. So thank you for watching for this one.